I'll begin by thanking the organizers for having me here. Um, and so I'm going to be talking about some things that is slightly off theme of the conference, but hopefully I'll convince you that this is also useful and potentially interesting for biophysicists. Most of my work is in learning and decision making in different contexts. So I've worked on different problems in animal behavior, thinking about navigation, uh, learning and decision making at the scale of single cells. And more recently, I started thinking about how machines solve problems. Right? I think this is motivated by this bigger problem of trying to understand what it means to be intelligent. Right? So the grand question is to define notions of intelligence and identify mechanisms for intelligence and really trying to understand what leads to intelligence. I think for a long time there is one way of doing that, which is to study natural brains. Right? So you would go down this bright and glorious path as a neuroscientist, and hopefully if you go further along, you figure out mechanisms for intelligence and you declare success. But in the last 10 years or maybe 5 years, we have a new opportunity in the sense that we now have machines that are intelligent. One can argue how intelligent, but I think we all agree that they are intelligent. So now you can take this other choice and try to figure out, to what extent we can understand how these machines work, and whether we can derive more general conceptual principles of intelligence. Right? So we're going to go down this dark and dangerous road. And I would really say that the field is quite new. And so I think we are not quite far into the road. We're like basically maybe here, right? So, but I'm going to give you some glimpse of where we are and where the field is, hopefully. Okay, so I'm going to focus on one particular phenomenon, which is called in-context learning. And in the spirit of showing ChatGPT prompts, I'm going to first show you an example of what I mean by in-context learning, right? So let's say you kind of prompt ChatGPT with this simple prompt. This is something that I made up, and the names are purposely complicated. So let's say A married B and C married D. Who did D marry? Right? It's kind of a straightforward question for us, and apparently it's straightforward for them too because they get the answer right. But if you really kind of think about what's happening here, it's quite remarkable, right? So they kind of understand the concept of marriage and the relationship, that it goes both ways, and that the name over here is really a label, right? The relationship is kind of conserved, but the labels can be interchangeable. And this is quite remarkable, mainly because the parameters of the network are fixed, right? So the way we used to think about learning, and this is learning because you're giving it new information that it has never seen before, it's learning, but there's no weight updates, right? None of the parameters of the model are changing. This is purely in terms of the activations of the network. You kind of, giving this input, you kind of have a flow of information, and then you get the output, which is this answer, right? So this was defined in this in the ChatGPT paper, which came out, GPT-3 paper that came out in 2020, and you can define it as a paradigm that allows language models to learn tasks given only a few examples in the form of a demonstration, right? So here the demonstrations are these examples. The key point being that there are no parameter updates when you do this. The other interesting aspect of this is that scale matters, right? So you can design various in-context learning tasks. So for example, you can have cycle letters. So you give a word and you cycle the letters by one, and you give a few of these examples. And you ask different models to kind of give you the answer for a new example. And it turns out that as you scale the number of parameters in these models, it just gets better, right? So this 175 billion parameter is GPT-3. That's the one that was the foundation for ChatGPT. And you can see that it's all monotonic, right? So scale does matter.
Gautam,
yeah.
Maybe a weird question, but I would have imagined, like, if you were to ask me what this plot would look like, I would have imagined not a gradual change, but something that was more sudden.
There are certain tasks where the performance is more abrupt, and certain tasks where it's more gradual. It also depends on what metric you use. In fact, one of your last student who was also featured, Ryland, kind of showed that. It can be gradual or abrupt depending on the task. So there's various questions in this field, right? So this is a kind of new paradigm, and you're basically training this transformer or large language model on a lot of data, and you're probing it on new tasks, and you can solve these tasks. And there's various set of, I think, big questions that one can ask. One is about scaling, right? So what do you really get when you increase the number of parameters of these models? There's questions of universality in the sense that if you train the same model multiple times, maybe on distinct data sets, maybe with different initializations, do you converge to the same solution? And we don't have answers to these questions, right? And these are really empirical questions, potentially theory questions as well, but these are open questions. Now, when we think about in-context learning in particular, there's a way of kind of designing a synthetic paradigm where you can hopefully make some progress. So these are like large models that are trained on a lot of language data, but you can train the same models on scratch from synthetic data. So now you have some handle on what data is going into these models. Yeah.
Can I just ask a really basic question? What is the learning? Like, in what sense is it learning if it's not updating parameters? What's it changing as it gets more examples?
The activations of the network are changing. So depending on the examples that you present, the processing that it does or the layers of the network will change. Yeah.
But it is a bad name, right? It's just in-context inference. Right?
Yeah.
It would be fine.
Yeah, it would be fine if you can call it inference. But yeah. It's learning in the sense that you're giving n examples and you're asked to predict what's the output for the n+1 example. Just the way that you give a data set, you tune some parameters, and then you ask for a new prediction. Yeah.
So, I mean, presumably, is everything we're asking ChatGPT that it's doing this behavior? Because I suppose on shorter time scales, the parameters are not being updated, right?
Yeah.
So is our daily interfacing with these chatbots basically in context learning, like anything that it shows there?
Yeah, so we're never changing the weights of the network. It's always, but in this case, you're actually giving examples in the form of demonstration for what task you should perform. And often when we are chatting with it, we're not often giving them demonstrations. So for example, like if you wanted ChatGPT to solve a math problem, one way to do it is to kind of give examples of different problems where the solution is given, kind of tells them what kind of answers you're looking for. And now you give a new problem that does not have a solution, and then it produces the right answer. In fact, when for instance Gemini is like asked to solve IMO problems or something like that, they very likely have a large set of prompts telling it what to do. That's different from fine-tuning the weights. Okay. So the synthetic paradigm is the following, and this is mathematically precise, so it kind of helps clarify some ideas, hopefully Michael's question as well, which is that what you do in these synthetic settings is to first define a function class. For example, this could be a class of linear functions with d-dimensional inputs. You have an input data distribution D. You generate sequences, and the way you generate sequences is that you first sample a function from this function class, some data from this distribution, and you generate labels, right? So what you now have are a sequence of n input-output pairs, and you feed it to a network that takes in sequences. This is going to be a transformer, and then you ask it to predict the answer for a new query. Okay, so this is what one sequence will look like when it goes into the transformer. This is the prompt. Yeah.
So you have, say, function class and labels, but clearly they're not one-to-one or something like that.
In what I'll be talking about, they are going to be one-to-one, but in general, they can be any function. I'm going to give you a few examples going forward, but this is a general procedure of how you train these models. Yeah.
Is this a new function f from the function class for each x, or is it the same one function sampled and then?
Every prompt, every sequence has the same function, but across sequences, you sample different functions. Okay, so the way you kind of feed this into a network is that, let's say you have x, which is d-dimensional. You construct a d+1 dimensional vector. The first d correspond to the components of x, and you leave the last one 0. And for the label, you keep the first d 0 and put in the label as the last component, right? And then you give a sequence of these vectors as an input. I'm going to explain later on what a transformer does, but for now, suffice to say that this is a model that takes in a set of inputs, in this case, this sequence, and produces an output, right? It's a prediction machine that takes in a sequence.
Gautam, so would first few examples? And
Yeah.
then train it?
Yeah, if you were to do it with an MLP, you would have to give like n examples as input and ask it to predict the n plus 1th.
Exactly.
But as you scale n, you're going to get a larger and larger network.
Yes.
But in this case, you don't, because the weights are all shared across the various inputs.
Yes, but I guess the baseline would just be that I train an MLP on the examples.
Yes.
On the n examples, and then ask.
Yes. Yeah, I'll show a couple of examples. And then you iterate this process, right? So this transformer sees sequences from all functions in the function class. You kind of have an essentially infinite data set, but because you can constantly generate functions and sequences given a particular function. This is called meta training. And this is what allows you to kind of get this capability. So if you do this for, let's say, a 10-layer transformer, and I'll again explain what a layer means in a transformer. So let's say, for example, the function class is a class of linear functions which take 20-dimensional inputs, right? So if you train this transformer, meta-train it, and now you test it on in-context examples. So let's say you give it 10 in-context examples and ask it to predict for the 11th one. It does just as well as least squares, which is the best thing you can do for linear regression. This is noiseless, so this is really the best you can do. So basically the transformer, even though it's not a linear model, it learns to emulate a linear model in the activations of the network, okay? It turns out that if the function class is a class of sparse linear regression models, you can use lasso, and you can show that lasso is near optimal. But it turns out that the transformer learns to approximate lasso within the activations of the network. In these two cases, you kind of have a sense of what is near optimal, but it turns out you can do this in cases where you don't know what's the optimal. So for example, you can give it data that is appropriate for decision trees, right? And for decision trees, there's various heuristics on what's good, but there's no optimal algorithm. In that case, the transformer actually does better than all of the standard algorithms for decision trees, right?
Just make sure I'm following. Like this transformer is been pre-trained. It's only after it's trained that you're giving it examples from linear regression as fast as linear regression.
Yes. Okay. Yeah. So it's kind of learning to emulate an algorithm that allows you to kind of.
Lasso has a parameter, right?
Yeah.
So you choose that, and then it emulates the best one that the lasso to the best fit or the best hyperparameter.
You mean the transformer or the lasso itself?
So how do you choose the lasso?
This is not our work, but I believe you kind of give it data with a particular sparsity.
Yeah.
And you train lasso in such a way that you get the best performance. So you kind of do the
And
validation.
That's what it's mimicking.
Yeah, it's mimicking the best possible thing you can do with the lasso. Yeah.
Gautam, can I go back to my earlier question? Like
Yeah.
whether or not I should be impressed by this, I think will depend on whether if I train an MLP on these same number of examples from scratch.
Yeah.
I can do better or worse. I don't know if it's beating that. Like I don't know if an MLP trained on the same number of examples will also do as well as least squares for linear regression and lasso.
So an MLP trained from scratch on 20 examples?
Yes.
Yeah, I think that baseline is not here.
Whether I should be impressed or not, right?
Yeah, I mean, I would suspect it takes a lot more examples to kind of train an MLP, but I'm not sure.
Not sure. Simple enough task.
Okay, it turns out that maybe this also kind of relates to your last question. You can train transformers from outputs generated from a randomly initialized two-layer neural network, and it matches what you would get when you do gradient descent using MLP. Right? So that's maybe more in line with what Ila said. But I do think it's still an interesting set of capabilities, right? In the sense that you don't have to kind of design an optimization algorithm to solve a particular problem. You kind of give a network a large set of examples, and in the end, it's going to learn an algorithm for you that's going to solve the problem of interest. Yeah.
So the function class that you had defined before, is that the network that you have already trained in, the F that you're sampling, is that
the samples are from that function class.
So the function class refers to the training model, or it is independent of that?
The training model is a transformer. It's completely independent of what function class is being drawn. In fact, in all of these examples, it's the same transformer. Like it's the same architecture. Okay, I'm going to be focusing on one particular aspect of this phenomenology. There's a lot of work in the last couple of years. If you notice, this paper was from 2 years ago, but this kind of spurred a lot of activity. And we kind of understand in limited scenarios what's going on. I'm going to focus on one particular thing that happens in these models, which is the transition from memorization to generalization. Okay? So I'm going to show you a plot that characterizes the phenomenology. And this is basically for a Markov chains. So you can do this for all kinds of data distributions. This in particular is for dynamical systems, Markov chains. So you kind of generate data from K, a finite number of Markov chains, and you train a transformer. So it turns out that if K is small enough, as you train a transformer, it learns to memorize these chains in the sense that it recognizes which of these chains, K chains, the data is coming from, and produces an output corresponding to those. But it turns out that as you increase the data diversity, which is this K parameter, at some point it transitions to generalization, in the sense that you can give it a chain that it has never seen before, basically a walk on some graph, right? That's basically what a Markov chain is, a random walk. It can start learning the structure of that walk on the fly and produce the right output, okay? So it's learning, I mean, in some ways a map of the environment, yeah. It's just the next token, right? So in this case, it's just going to be the next token, yeah. And this kind of, yeah. Yeah, these are trained autoregressively, so they see all subsequences as well. And you can show that when they get here, they're doing Bayes optimal on the data distribution that they're trained on. And over here, they're Bayes optimal on the prior of the data distribution that is generating the data. Okay? So this is really like they get to the optimal thing you can do. And there's two sets of questions that are interesting in this. And this kind of phase plot has been observed for many different tasks for different architectures. So this phenomenology seems to be conserved. Okay, so this kind of transitions. There's kind of two questions that I'll be focusing on. One of which is what determines K star, which is how much data do you need to give before it starts to generalize or learn the rule that kind of solves this problem in general. And the other one is what determines the transition from not generalizing to generalizing. And this transition often is abrupt in these models, right? So for a while over training, they're not doing anything. The loss doesn't move a lot. At some point, there's a sudden transition to basically zero loss or perfect accuracy. Yeah.
This vertical line, is it clear it's just about generalization? Because even for this, like, I don't know what the colors mean, but presumably on the left of this, you just don't have enough examples to do anything, and on the right of which you do.
Yeah, I mean, this is a fairly large number of steps. So each step has, a batch, and you're seeing many examples. So you see how you have data. It just so happens that there's a step-like transition there.
But then why is it at the bottom that, you don't get memorization sort of, like there seems to be some characteristic time that it takes.
Yeah, I'll talk, like that time scale will actually matter a lot in what we're talking about. Yeah. Yeah, so in this case, you're actually seeing the training process. The x-axis is the training steps. And they're not pre-trained, so 0 is actually from scratch. Yeah. Why it's not a straight line? Oh yeah, here the transition is sharp. Oh, like this? Yeah, so it kind of bleeds in. This particular paradigm, so this is also observed in most settings. We have unpublished work kind of characterizing these different points. So in some ways, there's a somewhat like a triple point over here, right, where these 3 different phases. So I didn't explain what this green one means, but we have a characterization of that. And there's something that determines this point. There's a K1 star, so to speak. And there's a K2 star over here, up to which the red kind of bleeds into the blue. We understand kind of where both of those come from, but I'm not going to talk about that because it's not kind of polished yet. Okay, any other questions? All right. So what we've done so far is to explain or characterize these quantities in a setting where we can basically do most of the math and most of the empirics. Okay, so it's a simplified setting, but it turns out that this minimal setting kind of captures most of the phenomenology. And we are now working on this particular setting, which is the next level of complexity. Okay, so I'm going to describe what that is. What we do is to first generate k items. So these items are just random vectors in a d-dimensional space. So you have k of them. And for each of these k items, we assign +1 or -1. So you give them a label of A or B, which here it's +1 or -1. So you have a finite data set of D, right? Item label pairs. Now each sequence that you give to the transformer is going to look like this. So it's going to have an item label, and so on. There's going to be n of them. And for the last one, you're going to ask what is the right label. And we have a rule that allows the transformer to solve it. It's kind of a fairly simple setting in the sense that there's always going to be a copy of the query in the prompt, right? So there's going to be a copy of orange over here or anywhere in between, but there's going to be a copy somewhere. And what the transformer needs to do is to produce a label next to it. The key point is that because there's a finite number k, it can also memorize if it wants to, right? It can learn that orange means +1 over training and just produce a +1. So it's a reactive kind of strategy where it doesn't care about what happened in the past. It just produces the right answer, right? So this is quite simplified, but this has a long history in the sense, not very long, but 4 paper worth of history in the sense that we had a broader phenomenology and kind of we distilled the phenomenology down to the simple setting, and which is why it looks kind of artificial. But this is what we need to capture the phenomena. Okay, it's just the point that there's a trade-off. There's a competition between a rule that you need to learn in order to generalize and memorization. Right, so that's the trade-off. Yeah.
Is the memorization part here the fact that 4 always comes with +1, or is it that I can always go in the past and look at what was, yeah?
The memorization is a fact that 4 always comes with +1. Okay. Yeah.
My understanding was with these transformers, the importance of these is when you have sort of long-range associations, etc.
Yeah.
Where do I see all of this? So why are we using a transformer here?
This is a long-range association, right? So in this case, like you can have a very long sequence. And this orange needs to look back on all the examples of orange in the past and then produce what orange is associated to, which is the next step.
But orange is not associated with yellows, pinks, etc.
Not in this task. Yeah, but you can do that. You can kind of create a data set that you want. This just turns out to be the simplest way to do this. Yeah.
There's no pre-training of anything, right? This is what they've seen so far, and then you ask.
Well, they're trained on many such sequences, right? So the pre-training itself is on these kinds of sequences, right? Yeah, the generalization is that you look at the orange in the context and produce a label corresponding to orange. That's generalization. Yes. Yeah. And there's like a way to kind of measure generalization and memorization in the sense that you can give it item label pairs that are not in the data set. And if it doesn't memorize, then if it generalizes, then it's going to be able to do it. And you can measure memorization by not giving the copy and seeing how well it does. Right? So there's ways of measuring memorization and generalization. It turns out that after the in-context learning papers in machine learning, someone kind of went and did these experiments in humans. You can set up essentially the same setting where you kind of you assign basically different images with labels. You give it in this format. In this case, the rule needs to be a little bit more non-trivial, which is that the image is going to be associated with a label 3 steps ahead. And then you give humans many such patterns and ask what is the label for the bear over here. So it's really the same setting. And it turns out this also produces the same phenomenology in humans. You see the same transition. Yeah. Sorry? That's the kind of punchline of this paper, of the experimental paper, which is that as you modulate K or some effective version of K, you go from learning the rule to memorizing the label. I mean, in this experiment, there's many such labels, many such images. So it really depends on how broad your data set is. All right. So it turns out that this task, you can kind of distill all the phenomenology into a 2-layer transformer. Okay, so that's the minimal size transformer that you need to solve this task. It's 2 layers of attention followed by an MLP, followed by a binary classifier. Okay, yeah.
What's an MLP?
Yeah, I'll explain that. So the next 2 slides, I'm just going to give some brief introduction to transformers. It's going to be kind of very coarse-grained, but hopefully just seeing the equations once will help you kind of align with what I'm going to say going forward. Oh, sorry, actually I have a slide showing the phenomenology first. Right, so this is the phenomenology. So as you modulate K and you plot the generalization accuracy on the y-axis, 50% is chance, and at some value of K, there's a transition from memorization to generalization. The other phenomenon that is of interest, which is this T star that I mentioned, is that if you look at the learning curves of these models during training, they have this sharp jump. These are 2 different seeds, so you're seeing 2 different independent realizations of the same process. They basically show chance accuracy, and at a certain point, there's a sharp transition to perfect accuracy. Again, this is a generic phenomenon in these models. Right? So we want to get K star and we want to get T-gen. Just as an aside, as I was mentioning, if you look at the data, what they modulate is some kind of ZIF exponent, the data distribution, and you see the same transition even in human data. Okay, so there's something more generic about this than just transformers. All right. Okay, so this is now the 2-slide introduction to transformers. So I'm going to describe what I mean by 1-layer transformer. It's basically 1 attention head and 1 MLP, a multi-layer perceptron, and then a classifier. Okay, so as I said, the transformer takes in a sequence of vectors, let's say U1 through U5. What the attention operation does is that it does a linear combination. It takes a linear combination of these inputs, right? So it's a seemingly linear combination of these inputs. So it takes a vector and adds a linear combination of whatever appeared in the past, except it's not truly linear in the sense that these weights depend on this attention weight, right? So it's some kind of dot product similarity, but instead of a plain dot product similarity, you get these query key matrices in between. Okay? And then you kind of write, you have another matrix, a value matrix, which extracts the right information from these vectors. Okay? I'm going to explain some intuition for what these operations mean later on. But effectively, you have to remember that there's 3 matrices that you're learning for each attention head, 2 of which determine what you're going to pay attention to, and 1 which determines what you're going to extract from those that you pay attention to. Right?
So where is the third matrix? Is it K1, Q1?
Yeah, there's K1, Q1, and V1. Yeah, key, query, and value. Okay, so once you do this, you're going to get a new sequence of vectors, V1 through V5. And now you pass them through, you only pass the last one through an MLP, okay? In this case, because it's a 1-layer transformer. And an MLP, a multi-layer perceptron, is going to look like this. It's a sequence of nested nonlinearities. So you apply a linear transformation, and then you apply a pointwise nonlinearity, usually a rectified linear function, right? So that's the MLP. In this case, we're going to use a 3-layer MLP, but that's not important. And once you do that, you're going to get a scalar output, which is the logit. And you can define a loss function, which is the classical binary cross-entropy loss, right? So if you're doing a binary classification, this is the loss that you would use. And so in practice, you give it a sequence, you compute the logit, compute the loss, and perform gradient descent to optimize these weights, W, and also these 3 matrices, V, K, and Q. Okay. So that's a 1-layer transformer. What a 2-layer model does is something a little bit more complicated, but in principle, it's really the same idea, right? So you have 1 attention layer like this. If you have 1 more attention layer, what you're going to do is to simply stack them, right? So you're going to apply the same operation, but with different matrices on the vectors that come from the first layer, right? So initially you applied this and you got your V vectors, and you're going to apply the same operation, but with different matrices, and you're going to get your Ws, which is the output of the second layers. Now, I just want to make one point with this math over here that I'm going to write down, which is that when you kind of plug the V's over here into over here, you're going to get like the same first order terms that you would get with a one layer model, but then you have this cross term, which is quite important. So what this cross term is telling you is that you can have a token that extracts information from some other token in the past, and some future token can extract information about both. So a one layer transformer forms basically pairwise associations, but when you stack these layers, you can form multi-hop associations. And that's what kind of depth really gives you over here, right? And that's kind of what is necessary to make it work in this task as well. All right, and then you kind of pass it through, get the logit by passing it through the multi-layer perceptron, and you train it using a cross-entropy loss. Yeah.
I think I understand what you said, but in the end, it's a matrix, right? Aij, Jk. So
yeah, but they're functions of the input, right? So they're not just matrices. All right. Any other questions here?
Maybe see the thing, but I mean, if I didn't have two layers, but instead of having an Aij, I had like something like a Bijk or something like that with one layer, would I essentially be, I mean, I haven't thought through how I would represent this Bijk, but like,
Yeah.
would there be an effective way to write down a single layer model?
Yeah, there's various tensor kind of generalizations of these attentions. There's all kinds of generalizations, including tensor generalizations, which are not very popular, but there's efficient ways of like implementing them and all of that. All right, so I mentioned that the two-layer model was the minimal necessary to kind of solve this task. Me and a few others kind of went through the process of doing experiments to figure out this mechanism. It was first proposed by a paper from Anthropic in 2022. I'm going to explain what this operation is. It's called an induction head, and you can think of it as a mechanism for zero-shot associative learning or copying, in the sense that when you give, let's say you're seeing a long piece of text and you see, let's say, X and Y, I don't know, like Harry Potter, let's say, and you see Harry again, but you've never seen those words anywhere in training, what's the best thing you can do? You're going to produce Potter, right? So kind of look back and kind of produce the next thing that comes up. And that's a form of zero-shot associative learning, and that's what an induction head does. It's almost like the simple harmonic oscillator of these models, in the sense that it always shows up. It shows up at important moments during training, and we understand how it works pretty well. Yeah. And it also gives some intuition for how to think about these models. Okay, so let's say we have an example prompt where you give a blue item, a label, a red item, and a label, and then now you ask what is the label for a blue item. The way to think about the representations of each of these objects is to assume that each of these objects has a subspace dedicated to position, so their position in the sequence, which turns out to be important. You have subspace dedicated to their content, right? So what they're storing, and a subspace that is initially empty, which you can think of it as a buffer subspace. This is not what you would give to the network, but this is how you can conceptualize the network. It's a cartoon version of the network, which is useful for getting some intuition. And you can assume that each layer performs a read and write operation. So the first layer of the attention first performs a read operation, and in this particular case of an induction head, each token or each input pays attention to the token that came before it. Okay? So it uses the query key matrices to pay attention to the token that came before it, and copies information about the content into the buffer. Okay? So the value matrix kind of does that operation. Right? There's a specific set of operations that happens in the first layer. In the second layer, the very last token uses its content to pay attention to whatever is in the buffer of all the other tokens. Okay? So now if you kind of keep track of how information has flown, this label that you need to be the answer, this blue item was copied into its buffer in the first step. And so now this buffer has blue. And so when this one uses its content to match with the buffer, it's going to pay attention to exactly the right label. And then it's going to extract the content of the label, which is, pink in this case, right? So it's kind of forming an association in the first layer. And in the second layer, the target is kind of extracting that association. And this is an induction head. And there's generalized versions of this that you can see in networks. So it's not, this is a simplified version of it, but you can think of the same kind of idea applying to higher level concepts. And you've seen that too. Yeah.
So in each of these layers, you're describing two things that are happening, right? So what are one of the two things happening is the Aij giving me the first step and the V giving me the second step?
Yes, exactly. So you can think of the querying key being used to read information and the value as being used to write. And each of those will look at specific subspaces, combinations of subspaces, and write to specific subspaces. There's a whole calculus that you can derive from this, which is an interesting exercise as well. And I think we should do as a field. Okay, one thing I should mention is that you can kind of know that this works by designing a synthetic transformer that just has this structure and nothing else. You kind of artificially kind of force it to interact with subspaces in a particular way and show that this reproduces all the phenomenology that I mentioned before, which is kind of clarifies that this is really what you need in order to get what you see. And there's various empirical tests you can do as well. All right. So let's get back to this, this framework, and I'm now going to kind of build some theory on top of the phenomenology that I just described. I mentioned that this is basically the operation for learning the rule over here. So you first copy something about an item to the label, and then you pay attention to that. That's the mechanism. So in fact, you can kind of simplify this, and even during training, you can kind of concatenate the item and the label together and give a sequence of concatenated item label pairs that kind of bypasses the first layer of the transformer. So what you get is really just a one-layer transformer model. You can kind of get rid of one layer in this transformer by giving it a simplified version of the input. And now we're going to do all of the math on this model, which we can understand pretty well. All right. So in order to do this, we're going to postulate like two ansatz. And it turns out even the simplified model is not solvable in general. So you have to kind of make these approximations that make it tractable. And the philosophy, of course, is in the spirit that you make these ansatz, you come up with some predictions, and then you test them empirically and see how well these predictions hold true. The first one is that if you look at this network, you have these two elements, the multilayer perceptron and the attention layer, kind of producing your output, right? So you have two independent subcircuits that are kind of coming together to produce an output. You can effectively assume that they're independent, right? So you have one subcircuit that is the attention head and the other subcircuit, which is the MLP. And the final answer is really just a sum of these two, right? So you basically have an energy function effectively, which is a function of these two subcircuits, but we're saying it's actually additive. Like you have the energy function from one plus the energy function from the other. That's basically the approximation that we make. The other...
But that's reasonable even though you're training them like end-to-end?
Yeah. Yeah, that seems to be reasonable, partly we think because the residual stream, so everything gets added. So there's a natural decomposition anyway. It's not exact, but it's still an approximation, but it seems reasonable because of that reason.
You could also break it, right? You could actually train the
Yes.
separately with these X.
Yeah, we did some of that too.
Oh, I see.
If you train it with just the attention layer, you're not going to see any memorization. If you train it with just MLP, you're just going to see memorization. All right, so the second simplification that we have to do is something that we call the interaction strength ansatz. It's not really an ansatz, you can actually derive it. It turns out that when you look at these attention heads, you have three matrices. It turns out that only two parameters in these matrices actually are unstable in the sense that most of them remain stuck at 0. And so you get effectively two quote-unquote order parameters in this model. Everything else doesn't matter. So you can describe the dynamics with just two parameters. It's just two parameters that matter. And specifically, reducing this model down to 2 parameters is equivalent to setting this query key matrix as a diagonal in the first D by D matrix and 0 everywhere else. And the value matrix has a W over here, right? So you can kind of formalize this statement. The reason this happens is because you have various symmetries in this problem in the limit that when the data size is infinity, and you can show that these are the only quantities that kind of grow during training. Okay, so you only have 2 effective parameters that matter. And once you kind of simplify this part of the network, you get a relatively simple expression for the attention head. So what this is essentially saying is that you have a dot product similarity between your target and your everything else in your context. So that's the dot product, which is weighted by some strength beta. And if beta is large enough, you pay attention to the right item, and then you copy the right label with the W parameter. Right? So you want beta and W to be large if you want to generalize. Okay? All right. So with these 2 ansatz, you can write down a loss function for this process. Okay. So you can write down, you can characterize the loss landscape. You have 2 parameters here, but you also have a set of parameters that come from the MLP. It turns out most of the parameters in the MLP don't matter. What actually matters is the distribution of outputs from the MLP over your data set, right? So that's really the distribution is what kind of goes into your loss function. So you have this kind of expression over here. And so, I mean, even though it looks kind of, heavy, it's quite interpretable. Like this is what you get from the attention head part of the network, the subcircuit that corresponds to the attention head. This is what comes from the MLP. And it turns out that it's quite important to put in fluctuations in the input as part of the loss landscape. These fluctuations come because when you're sampling item label pairs from your data set, you can sample by chance more +1s than -1s or more -1s than +1s. And if you don't put in this factor, you don't get the right dynamics, right? So these kind of minor fluctuations do matter close to initialization. These fluctuations are just in the statistics of the input. The +1s is just binomial noise, right? And in the larger limit, it's going to be Gaussian. So this is what the loss landscape looks like. And this is also true for the induction head. You basically get a flat part close to initialization. So this is where your system is going to start. And there's going to be a plateau in the beginning. And at some point, it's going to transition into this cliff. Okay, this is the origin of the sharp transition in your training dynamics. And the reason you get these sharp plateaus is because of these exponentials in the loss landscape. If you look at this loss landscape, you have a sigmoid over here. So you basically have an exponential of an exponential. When you have 3 layers, you get 3 nested exponentials. And what that's going to give you is a flat part and a very steep part. And that's the reason you get these sharp transitions. There's no magic to it. It's just the fact that you have nested exponentials. In this case, you can expand around initialization, and you can characterize the dynamics close to initialization. It turns out that when you stare at these equations, you would expect to see a saddle point for various reasons, but in fact, it's not a saddle point. There's a slight tilt towards the right part of this landscape. So the system is going to deterministically go down here, but it's go down very slowly at initialization. So the landscape close to initialization is quite flat, such that there's exponential dependence on the initial value. Okay? And you can characterize most of that. Okay, and there's one more parameter that comes out once you do this analysis, which we call the memorization order parameter, in the sense that there's a C1 over here. And this C1 is effectively the number of examples that have not yet been memorized by your MLP, okay? So the way to interpret that is that you have your generalization mechanism going on. It's kind of updating its parameters, but the only signal that you get is from the data points that have not yet been explained by the other subcircuit, right? So every time you're learning something, the only signal that you're going to get is something from the unexplained part of the data set, and that's what scales the learning rate over here. And at this point, it's kind of, I think, useful to kind of delineate the two hypotheses that we were trying to distinguish. The first is some notion of capacity constraint, right? So you can imagine that these networks, though they're quite complicated, as you increase the size of the data set, you're somehow capacity constrained. You can no longer memorize the data set. So initially you could memorize them, and memorization always gives you zero loss. So you prefer memorizing over generalizing. And at some point, as you increase K, you have these kind of energy landscapes that shift, and you start preferring to generalize and not memorize, right? So that's one hypothesis. It's a capacity constraint on the network. The other hypothesis is that it's a kinetic competition in the sense that it takes some time to memorize, it takes some time to generalize. These two are completely independent processes, but once you memorize, you can no longer generalize because you've explained most of your data set. And if you generalize, you don't no longer memorize because you've explained most of the data set. So it's a kinetic competition between two independent mechanisms. And we can test these hypotheses in this model. Yeah. So in this case, you have some kind of capacity constraint. And in this case, you have two independent circuits, one of which is memorizing, one of which is generalizing. If you memorize, then the loss is zero. There's nothing left to explain, so you no longer generalize. And if you generalize first, the loss is close to zero, and you no longer memorize. It's a very simple thing, but it's really distinct hypotheses, right? Yeah.
I mean, in principle, at some point you are going to become capacity constrained as you
Yes.
cross K, right? So I mean, I guess the claim about the hypothesis here is that
Which one comes faster?
yeah, exactly.
Yeah, that's exactly right. It's about the rates of learning, right? So you have two subcircuits that are learning independently. So it's not about double descent or anything like that. This is essentially saying that you always can memorize. It's just that you're memorizing too slow when your data is too diverse. All right. Okay. So in this simplified model, we can quantitatively test these sets of hypotheses. You can calculate how much time it takes to generalize. It turns out to depend on the number of input-output pairs that you give during training, which is n, like the number of examples in a single sequence. And it depends exponentially, as I was mentioning, on the initial value of one of these order parameters. So there's exponential sensitivity to the initial conditions. And you can characterize the time to memorize as the integral of the C1 parameter that I mentioned. Okay? So that's just the quantity that comes out. This turns out to be the right quantity to measure if you want to compare these time scales. Now, the first hypothesis is that for a certain value of K, this diverges, so it can no longer memorize. The time to memorization is infinity, in which case it's always going to generalize. So that's a capacity constraint. The other hypothesis is that at some point, this is finite, but these two actually match, and that's what determines your threshold value, right? So in the second hypothesis, in the kinetic case, you can match these time scales and get a prediction for what K star should scale with these various hyperparameters of your problem. Okay? So that's a concrete prediction that we can test. And that's what we're going to do. We can go back to the full transformer and test these predictions empirically. The first prediction is that the time to generalization scales linearly with the context length, so n, and also it has exponential dependence on beta 0, which is normally distributed, so it's log normal. That's precisely what we get. So if you run many simulations of this transformer for different values of n and initializations, you get this linear scaling, and you also get these really long tails because of the sensitive dependence on beta 0. You get one more prediction, which is that close to the transition, you should see solutions that are bimoral, in the sense that if you just generalize, you kind of don't memorize at all. And if you just cross the threshold, then you're going to generalize and not memorize. And depending on the initialization, you can fall in either class. And so you should see a bimoral set of solutions close to the transition. And that's precisely what you see. So if you kind of generate many seeds close to the place where you see the transition, you get effectively a bimoral distribution of generalizing solutions. In some cases, it never generalizes. In some cases, it generalizes quite rapidly. And I think the most non-trivial prediction is this matching of timescales that I mentioned, right? So you can get a scaling relationship between your K star and your N. So what happens here is that this does not diverge in the regime that we are interested in. So it's not capacity constrained, right? So it turns out that this value is actually finite. And if you measure it for different values of K, this value scales as a power law of K with some non-trivial exponent, which is 0.72. Okay? We don't know why this exponent comes about. This is just an empirical thing. You train an MLP to memorize labels, increase the size of your data set, and this is apparently how much time it takes to memorize a data set of size K. So the prediction is the following. So if you plug this back in over here, you get a pretty non-trivial prediction that the transition happens with context length raised to some 1.4, right? So it's quite a non-trivial prediction. And you can do this experiments where you measure your K star for different values of N, and this is precisely what you get in your kind of simulations, right? So it's quite close to what we predict. Okay, so that's pretty much what I have. I'll just conclude, give you a short list of insights that we got from this analysis. First is that you see these transitions, abrupt transitions, happening quite often in these models, and these happen due to these nested nonlinearities in the sense that once you kind of lock in the right mechanism, which requires multiple layers, you basically generalize perfectly, but before you do that, you basically don't do very well. And that locking takes a while, but once it's there, the loss goes to zero. That's why you see the sharp transition. The second one is that even though these networks are very complicated, it seems like, at least in these simple scenarios, you can kind of decompose them into distinct subcircuits and start thinking about each subcircuit independently. And when you start putting them together, you can think of the subcircuits as if they're competing to explain the data, right? So you have kind of different computations trying to explain the same data, and there's different ways that they learn to explain the data, and there's a computation that selects which one you will see in the end. And it's a relative rates at which these subcircuits learn. It's not the capacity constraint, which makes sense because these networks are huge. So you would think that they have pretty large capacity. So the dynamics does matter. Okay. So I'll just mention Alex, who led the second part of this work, and funding sources. Thank you. Yeah. Single layers, it's going to be not good at memorizing. A single layer will be a linear layer, and for the K values that we're looking at, which is 10 to the 4, a single layer perceptron is not going to be able to classify them perfectly. Yeah, it's quite possible that if you simplify the network to simpler than 3 layers, you actually hit the capacity constraint first. So it potentially does depend on what you pick. But in these large models, you have like 10 layers, right? So we're kind of splitting it up into different subcircuits. Yeah.
Maybe to go back, like earlier when you were showing us a phenomenology of this K star region, you talked about a K1 and a K2.
Yeah.
Could you say a little bit about that?
Yeah. Yeah, so there's a K1 over here, in the sense that beyond that K1, you first see generalization. And there's a region between K1 and some K2, where after you generalize, you eventually kind of degrade to memorization, right? So that's this part. And beyond a K2 star, you generalize and you never degrade to memorization. And this K1 star, we think, is a kinetic competition. So whichever appears first is the one that you select. This K2 star is a capacity constraint, because at this point, your K is so large that you can't fit it into your network. Yes.
So I guess, again, just probably a misunderstanding, but in some ways it would matter how you train, which way it goes as
Yeah, presumably. I mean, the learning, the way you present the data matters quite a lot. And I think one thing that we learned from this analysis, and this and other ones that we're doing right now, is that there's subtle differences in how you train and the data distribution that matter close to initialization, right? They can tell the landscape in ways that lead you to particular solutions. And it's quite non-trivial to figure them out until you kind of go through the math. Yeah.
Gautam, what is the effect of network size in the way that you showed us the in-context learning performance scaling in a non-trivial way with network size? But
Yeah.
that parameter didn't come into your theory as far
Yeah,
as
we haven't done that yet. That's something that we want to look at for this setting, for the Markov chain setting, which makes more sense, which is a little bit more complicated. We don't have so all of these kind of experiments were from well-layer networks, and there's no manipulation of the size. They just picked a large enough one. For linear regression, folks have shown that if you start with a one-layer network, it's equivalent to doing one step of gradient descent. That's how well you do. If you do two layers, you do two layers of gradient descent, but the learning rate is adaptive, and so on. So at a certain point, you basically are emulating certain k steps of gradient descent, adaptive gradient descent.
And in your theory, like in your later part, there's no end of
No, one limitation of the theory at this point is that we can do one-layer transformers, and we can do now two-layer transformers as well. But beyond that, we have to kind of make assumptions about various things. We don't have a way of doing theory beyond two.
Okay, let me ask one more. So this beta W picture that you had, right? That insights came from the experiments in the sense when you were doing, you kind of saw that you are sort of concentrating your weights in this particular way, or was it some?
Yeah, in the first iteration of this, it was experiments. In the second iteration, we did some math to show that this is what yeah, you can write down. You can show that you can write down a conservation equation in some sense and show that that's the quantity that grows during training. Yes.
Can you provide some indication from how parameters are, what is doing the generalization?
So the beta and W are the generalizing parameters. So they start from 0, and they have to both become large and positive. And the memorization parameters, I kind of abstracted them out. And when you do the math, they all kind of summarize into this one quantity, which is the probability of getting the wrong answer in a particular input, averaged over your data set. And so it kind of collapses into, like two quantities for generalization and one quantity for memorization. Yeah.
So in the real case of like ChatGPT or Gemini, it's a little bit more like complex than this, right? It's like, even for that like marriage question, it's probably memorizing the concept of marriage.
Yeah.
But kind of the problem is kind of like, so in that sense, the K is true, but it's not making a fair comparison. Right? My question is there like more empirical data for these kind of complex situations?
Yeah, that's a very good question. That's something that no one has done yet. There's some evidence of how these computations happen in the really large models. There's some work from Jacob Steinhardt in Berkeley trying to dissect how particular computations are performed. And in those cases, we understand the subcircuits that, circuits that do these computations. But one interesting question is to kind of generally frame this problem of, you specify the relationship between two entities, other two entities, and you ask a question about the relationship between these various entities, some kind of, what neuroscientists call a cognitive map in some sense, right, in the relational sense. We don't know if there's a generic set of mechanisms, if there's distinct mechanisms, whether we can, extract them from these models. We don't have that yet.
I mean, even for the smaller transformers, can you truncate using like smaller data sets of networks?
Yeah, the smaller transformers are actually pretty bad at that task. Yeah, so we've trained so it turns out that most of these interesting things, they actually can solve once you go beyond 10 billion parameters. And even then you need to fine tune them. Below that, they actually don't get the right answer. So the scale does matter quite a bit to see the phenomenology. That's part of the problem. Yeah.
Actually, maybe related to that. So I guess the way the scale that came in your picture was this D, right?
Okay, here the scale is really about data.
No, I meant in the how many parameters.
Yes, yes, yeah.
But in the end, the D didn't show up in your theory.
No.
So there, in principle, even if you had smaller things, it would have the same phenomenology. Like for this task.
Yeah, so the D also goes into the size of MLP, the width of the MLP. And so if D was really small, it's possible that the MLP cannot memorize. So it comes into the memorization capacity. All right. Thank you.